Hey, can everyone hear me? Welcome to our session on Newton's three laws. Well done, as always, for everyone, to everyone for making it on a Sunday. That's a really good effort. I'm really looking forward to today's one, actually. Newton's three laws is one of these kind of fundamental bits of physics. It's not, I mean, it's kind of a topic, but it's also a thing you'll learn that you'll then use in so many other parts of the A-level physics course. So this is almost as much as a tool as it is a separate topic. You're going to want to know Newton's three laws wherever you go inside AS or A-level physics. All right, so hopefully the stream is all working okay. Just need to edit one quick thing. There we go. Okay, so as I said, today is on Newton's laws, and I think we may as well just get started. Okay, so hi everyone. Yeah, feel free to say hi in the chat. And in terms of like how this is going to work, I'm going to take us through essentially a lesson. There's going to be two halves to the lesson, and after each half we'll do some exam questions. And I'll be talking through it. I might ask you some questions for you to answer in the chat, and that helps me see if you're kind of understanding and check that we're all on the same page. But also, if I say anything it doesn't make any sense to you, just pipe up in the chat and let me know. And as long as we have time, I'll kind of backtrack or try and explain things in a different way. All right, let's get started. I'm really hyped for this one, Newton's three laws. Okay, so a little bit about me. This is a picture of me against another moving picture of me you can see in the corner. My name is Matt. I'm the lead physics teacher here at Snap Revise. Outside of that, I'm a physics PhD student and have been tutoring physics privately for a long time now. All right, so that's me. And now this is us. So here's our objectives, and it's all about Newton's laws. Really is a fundamental bit of physics. We're going to state and explain Newton's three laws. Okay, there's three of them. We're going to calculate resultant forces, and we're going to determine if systems are in translational equilibrium. So we're going to define what that means and then use it to help us answer exam questions. And then we're going to solve a load of problems, all of which involve typically some special but quite common types of forces you see in your day-to-day life. Forces like weight and forces like reaction forces from being in contact with things. All right, so that's our three objectives. Let's get ourselves started. And usually before we do like the main content of the session, we'll just review a couple of things, a couple of tools that will be handy to already know about. No worries if you don't, because we're going to review them here. So just a couple of things. We're going to be working a lot with vectors today because forces are vectors. We will actually talk a little bit about free fall today. Okay, so forces are vectors, so we're going to need to know about these, and we're going to need to know about how to add vectors together. So the typical technique for adding vectors together, let's say I want to take this one on the left and I want to add it, I want to combine it with the one on the right-hand side. What I have to do is I have to take one of them and I put the tail of that one on the tip of the other one. So I'm going to take this whole vector and transport it over here and attach it like this. So I connect one end of one vector to the beginning of the next. Okay, so let's imagine we have a vector to the right of size 2. Let's imagine we have a vector to the left of size 1. Okay, so vectors are things that have a magnitude and a direction. When we add them together, we'll be going 2 to the right-hand side, but then we've got this 1 to the left-hand side. So altogether, the new thing, which goes from the beginning of the path to the end, this new vector is the resultant, what we get from adding them together. And this is something of size 1 to the right-hand side. All right, okay, yeah, hi everyone. Okay, sweet. So that's adding vectors together. We also need to be able to take any vector we have and split it into two independent directions. This is actually going to be really important today. So let's imagine I have this vector here. It has some size. Let's call it the length. It has some size called the length, and let's call that L. Let's say it's at some angle theta to the horizontal direction. Okay. It is very common in solving problems practically to need to split a vector into two parts. Say, for example, a horizontal bit added in the sense that we were just talking about before to a vertical bit. So here's two vectors, a horizontal bit, let's call it LH, a vertical bit LV, and when added together, they give back the original vector. Okay. How can I calculate the horizontal component of this vector? What is this length LH to the right-hand side? So the hint here is this is something to do with trigonometry. Trigonometry is always about knowing some angles and some lengths in a triangle and figuring out some of the others. Okay, so you may remember that cos theta is always equal to the horizontal over the hypotenuse, which is this long one here. So the horizontal component here is always given by the length multiplied by cos theta. Yeah, good, absolutely right. L cos theta, really nice. And the vertical bit then is going to be L sine theta. So that's a fact that we're going to use a lot today. All right, cool. And then people were already mentioning a bit about the acceleration due to gravity. And we'll talk about this more in the main session, but I think it's worth already just reminding you that in fact, everything on Earth, if you ignore air resistance, pretty much falls to the Earth at the same rate. That is, if you drop these objects at the same time, even though they have different masses, they will still fall towards the Earth with the same velocities and in particular, the same accelerations. So there is one unique thing called the acceleration due to gravity. It's often given the symbol g, and numerically it's 9.81, and the units are meters per second squared. We'll actually, in some sense, derive or talk more about this later in the session. But those are the things it's good to keep at the front of your head for today. All right, so now what we're going through is absolutely core material for all the main exam boards. So there's the AQA spec points we're doing. There's the OCR ones. And there's our EdXL ones. Okay, and I think we're really in a good place to get started. In the second half of the session, we'll look a bit more Newton's third law, but right now let's talk about Newton's first and second laws. And the second law kind of implies the first law, actually. Nonetheless, let's begin with the first law, because it's conceptually the big shift. Okay. Newton's first law states the following. Feel free to race me to it in the chat or phrase it in your own way. Newton's first law states that an object will remain at rest, or at constant velocity unless acted on by a force. Unless acted on by a, and I'm going to put an extra word here, which is going to come up a lot today, resultant, unless acted on by a resultant force. So ignoring that word for now, if we have an object and nothing acts on it, and it was at rest, it will stay at rest. Okay, nice. Slightly more surprisingly, if we have an object that is moving at some velocity and nothing acts on it, it will continue to always move at that velocity. It won't slow down on its own accord. Okay. And a key thing here also is that, like, you can have some forces acting on an object, but just so long as they balance out on each other so that the total force is still zero, so that there is still no total force, then again, an object will remain at rest or stay at constant velocity. So an example would be something like a book here. It has no velocity in any direction. And you can think about in the horizontal direction for this book. Okay, in the horizontal direction, nothing is pushing this book. No one is pushing it to the left or to the right in any way whatsoever. And so it's currently at rest and it will stay at rest. Now, in terms of that word resultant, and we'll look at this in more detail later in the session, there are a couple of forces acting on this book. There's the kind of weight of gravity pulling it down. There's a reaction force pulling it upwards. But here, these two things, this weight and this reaction, balance out so that the kind of total force is zero. And as a result, the book which is at rest will still stay at rest. There's no resultant, no total force on it. Okay. Now, maybe a slightly less intuitive example is thinking about something that's already moving at some velocity. Because we know from our experience, if we throw something through the air, it will typically slow down. But that's because of a cheeky force that actually already exists on Earth called air resistance. Now, if we imagine somewhere where there isn't air and there isn't air resistance, for example, in space, there we can really see this idea in action. So imagine you have some kind of asteroid, and imagine that at the moment it's moving along with some velocity v. Now, it could be that it bumps into some other rocks, but assuming it doesn't and it keeps moving through space, its velocity will never change because there's nothing out there in space to act on it. So there's no resultant force on this object, so it will just keep on moving at velocity v. Now, instead, if this was a much smaller rock that we can imagine now as being something that we've actually thrown through the air on Earth, then when something moves through the air, it feels a resistive force from the air. And that's the thing that would slow it down and cause its velocity to actually change. Okay, cool. So that's Newton's first law. Something will keep on moving just how it was unless there is a total force on it. Okay, and we can see this in more detail in Newton's second law. So what does Newton's second law say? Can anyone say it as an equation? Because I'm going to write it as a sentence to start with, and I'll write the equation later. So Newton's second law as a sentence says the resultant force, there's that word resultant again, on an object is directly proportional to acceleration. Okay, whenever you hear proportionality in a sentence, that means you're about to write down a formula. And great, I can see the formula in the chat. You're absolutely right. It's F equals ma. So we'll write that in a second. It's directly proportional to its acceleration. And the proportionality constant here is going to be what we call m. So the law in maths says F equals ma. So indeed, we see there's this proportionality between force and acceleration. You could have literally said Newton's second law as the resultant force is equal to the mass times the acceleration as well. That would have been absolutely fine. Okay, so as for the units here, well, the mass is typically given in kilograms, not grams, but kilograms are the standard unit. Acceleration is usually given in meters per second squared, and force we're used to giving in newtons. But from this formula, there's another unit we could give the force as well. We could also call this kilogram meters per second squared, just by combining the two units on the right-hand side. Okay, good. So let's start looking at some examples of using this idea. And again, don't forget this keyword resultant. Resultant means total. It's not any old force, which is equal to mass times acceleration. It's the total force, which is mass times acceleration. All right. Okay. So let's write this here as well. The resultant force is the total force. And when I say total, I mean given by vector addition. So remember, I was saying at the start, forces are the kinds of things that are vectors. They have directions and magnitudes. So when I say find the total of two forces, I mean add them as vectors and see what you get. So let's look at an example. We're going to use Newton's second law to figure out the acceleration of this box on the bottom left of the page. Okay, so what's the resultant force here? Let's call it F. And let's choose the right-hand direction to be positive. Yeah, absolutely right. Good. So the total force here is 6 newtons to the right-hand side. Why? Well, we've got this 10 Newton force to the right. But then when we vector add, we would take this other 4 Newton vector, put it the other way around over here. Whoops, I can't write an n today. There we go. So we would have to take away 4 to get a new vector of length 6 to the right-hand side. So the total force, the resultant force, is 6 newtons to the right-hand side. And then Newton's second law says F equals ma. Well, this is the resultant force. Okay, so the acceleration is going to be the 6 Newton force divided by the mass. The mass here is 5 kilograms. So it's going to be 1.2. Remember, acceleration was in meters per second squared. So there we go. We've already used Newton's second law in a particular case to figure out how an object's going to move. And we'll see plenty more examples like that as we go on. Nice, yeah, 1.2 meters per second squared. Sweet. Okay, so there are some particular types of force that come up a lot in Newton's law questions. In particular, they're forces that we experience a lot, things like weight. Okay, so weight is the downwards force due to gravity. Okay, cool. And how does this force work? Well, there is a formula for it. We had this symbol G before, which we said was 9.81 meters per second squared. The formula for weight is we take an object which has some mass m. The downwards force due to gravity, called W, is always given by that mass times G. Okay, which is 9.81. Now, this is quite interesting because imagine there was no other force on this object. W equals mg, exactly. The weight is equal to the mass times the gravitational field strength, G. Good. Now, what's kind of funny about this is if we use Newton's second law, we know that mass times acceleration will be the resultant force. If the only force is weight, i.e. if there's no air resistance, then the resultant force is the weight, and the formula for weight is mass times G. So altogether, we find that for any object, ma equals mg, and that's where you can derive this kind of weird outcome that since the mass divides out of this equation, the acceleration of any object is always this number g. So that's kind of weird. We've managed to predict here that any object will accelerate to the ground at the same rate, as long as you ignore air resistance. Once you include air resistance, the story changes. Okay, great. So we know that F equals ma. We know that an object will keep on moving in the same way it always was or stay still so long as there's no resultant force. We have a kind of concise word for this idea. We call it translational equilibrium. So we say, we have a special word for when the force is 0. We say an object is in translational equilibrium if, let's just find our pen, if the resultant force is 0. Now, we already know if the resultant force is 0, that should mean we keep on going at a constant velocity. We can actually see that from the second law. F equals ma, but imagine the force is 0 overall. That would mean ma was 0. But if ma is 0 and your mass is not equal to 0, that must mean your acceleration is equal to 0. And if your acceleration is equal to 0, you're going to have a constant velocity. Okay, cool. Now, often the kind of handy thing about translational equilibrium is it will help you figure out some unknown values in a force diagram. So a classic example would be something like this diagram here. And this diagram here is kind of interesting because there's 2 dimensions going on. We've got things going on in all sorts of directions. So I should mention this law F equals ma works in any direction. The force at some angle theta in that direction there, as a total, the force along some line is always going to be equal to the mass times the acceleration along that line as well. So you can use this law in any direction you like. But typically, you take a problem and you'll split it into a vertical version of the problem and a horizontal bit. So let's say that I tell you the system we're looking at here is in equilibrium, and I mean translational equilibrium. Now, as I'm telling you, the force in any direction is 0. Now we should actually draw in an extra force here. We've got some mass of 7 kilograms, which means we've got some weight here of 7g. So if I tell you this system is in translational equilibrium, that's going to give you a couple of equations, and we can use those equations to figure out these unknown values on the right-hand side, this size of a force T and the angle it's acting at theta. So let's see how we can do it. And what we need to do is split the problem into 2 parts. We're going to start by looking at the horizontal force. We're in equilibrium, so the horizontal force should be 0, but what do we have? Well, let's take the right-hand direction as positive and take upwards as positive too. Then, okay, in the right-hand direction, we have t cos theta. And then we add that to the 14, which is in the other direction, so we need to take it away. That'll be 0. So in other words, t cos theta equals 14 newtons. That's what we must know to be true if the force in the horizontal direction is 0. Let's look at the vertical direction. Here, the vertical component of our force here, TV, that's going to be t sine theta from the stuff we looked at earlier. So this time we'll find that t sine theta, well, for the vertical force to be 0, that needs to balance the weight, and the weight here is 7g. Okay, so now we've got 2 equations, and whenever you have 2 things you don't know, you'll need 2 equations to figure them both out, and that's what we now have. So, okay, we can combine these, and there are all sorts of ways you could combine these 2 equations. Let's call them equation 1 and equation 2. Whenever one's got a sine and one's got a cos, a quick way to solve these equations is to divide one by the other. So if you divide equation 2 by equation 1, you'll get t sine theta over t cos theta, but the t's will cancel out there, and sine theta over cos theta is the same as tan theta. Okay, on the other hand, when we divide equation 1, and I should have written it here really, equation 1 by equation 2 by equation 1, sorry, that's the same as doing the 7g here divided by this 14. 7g over 14. Okay, so we've managed to get a new equation. Tan theta is 7g over 14. You can take that equation and rearrange for theta using the inverse tan, and you'll find that theta is around 78.47 degrees. Okay, good. Now we've managed to figure out one of the values. The other one will be much easier. We can take the first equation, for example, and we can say, okay, well, t is the thing we don't know yet. And this is 14 over cos of theta, but we already figured out theta. It was this 78.47 degrees. So we'll chuck that in a calculator, and we'll find that the tension is around 70.08 newtons. Okay, good. So using the idea that the total force is 0, we managed to completely figure out what this extra force T theta here was. Typically, you can imagine this was like the tension in a rope or something. All right, so let's have a go at some example questions. But actually, how are we all feeling? This is making sense so far. Anyone have any questions? Seeing a 1 and a 2. Okay. Okay, sweet. Well, let me know if there's any questions. In the meantime, we have some questions we can have a go at. This first one's quite interesting. It asks us to define a Newton. Whenever you're asked to define a quantity and you don't know what to do, think of the equation where that quantity appears. So for us, Newton is a force. Force appears in F equals ma. Now, if I want to define the Newton, that is the unit of this thing here, all I do is I say one of that thing is what I get when I make everything else in the equation 1. So here I would say 1 Newton is the force on a 1 kilogram mass with an acceleration of 1 meter per second squared. So see, I just replaced everything else in the equation with 1, and then I could use that to say what 1 Newton would be. Okay, part B. Figure 3.1 shows a spaceship on the surface of the Earth. The mass of the spaceship is 1.9 times 10 to 6 kilograms. During liftoff, the spaceship rockets produce a vertical upwards force of 3.1 times 10 to the 7. Whenever I'm reading these questions, I always label any missing information as we go. All right, and I'm actually going to write it again on the next page. So we've got this thing here, this rocket, it was 3.1 times 10 to the power 7 newtons. And we were also told a mass. The mass was 1.9 times 10 to the power 6 kilograms. Okay, 9 times 10 to the 6 kilograms. Okay, they ask us to calculate the weight. Now remember, the formula for weight was W equals mg, where m was the mass, so that's 1.6 times 10 to the power 6 kilograms. And g, that's the acceleration due to gravity, which was 9.81 meters per second squared. So you can chuck that all in a calculator, and we're roughly multiplying by 10. So it should look pretty much like the previous answer with an extra power of 10. Indeed, if you chuck this in a calculator, you'll get 1.867, etc., times 10 to the power 7, which is roughly 1.9 times 10 to the 7. So pretty much we've just multiplied by 10. Okay, and now here's the kicker. We're going to use this Newton's second law again to figure out acceleration. They ask us to calculate the initial acceleration. Well, we know that the acceleration is going to be the total force divided by the mass. But what is the total force here? Well, we have an upwards force. So let's take upwards as our positive direction. We have an upwards force. It's 3.1 times 10 to the power 7 newtons. But we also have this downwards force, which we just showed was 1.867 times 10 to the 7. The weight is pulling this mass downwards back to Earth. So we need to take that off to find the total force, 1.867 times 10 to the 7. Notice I used the unrounded answer for now, so we can round again later instead. And the mass was 1.9 times 10 to the power 6. Shut that all in a calculator and you'll get around 6.5057. And that'll be meters per second squared. And roughly speaking, we can round that to 6.5 meters per second squared. All right, good. Okay, so now let's work with one of these more vector style questions where you have to think about more than just the vertical direction. And there's a kind of extra lesson in this question. Okay, figure 4.1 shows a method used to knock down walls. Okay, so we've got some crane. It's going to hold up some kind of a ball. Could I use the value of a equals 10 for acceleration? No. So as a sanity check, I was happy to see that my answer was about 10 times the original one. That meant I probably didn't make a mistake in the calculator. But you are expected in your exam to use G to 3 significant figures. So you need to use 9.81. But it should always, your answer will look like roughly 10 times what you started with, and that'll be a sanity check. But yeah, no, you do need to use 9.81 in the calculation, unless it's an estimate. Good. Okay. So M here is a heavy steel ball suspended by a cable in which the tension is T. The ball is pulled to one side by horizontal force F until the cable is at 30 degrees to the vertical. It's then released so it swings to the wall. Okay, the weight is so much. Determine the force F using a triangle of forces or a scale diagram or by resolving forces. Hard for us to use a ruler here, so we're going to do it with maths. Okay. And the key thing here, it's kind of implicit in the question, but they've like slowly brought this ball up and they don't mention it, but I think essentially the intention of the examiner is to say, and then it's kind of held there and then they let go and it hits the wall. So the assumption is that at this position, the ball is just kind of staying there in position. In other words, it's not moving. In other words, at this second, it's in equilibrium. And if we didn't know that, we wouldn't be able to solve this question. So sometimes if you're missing equations, it might be that the examiner wants you to assume that your system is in equilibrium, even if it hasn't quite been explicitly said in the question. Okay, so assuming equilibrium, we have two equations. We know the vertical force is in total 0, as is the horizontal one. Let's start with the vertical force. In the vertical direction, we have this 30 degrees here. And notice here, this 30 degrees is up here. So actually the vertical component of our force, of our tension, this part here, you can see that's actually T cos 30 here. And the horizontal bit of this force is actually T sine 30. Okay, so in the vertical direction, we have T cos 30. And we know that must balance if we're in equilibrium, whatever's going down, and what's going down is 2000 newtons. So altogether, that tells us the value of the tension. It tells us the tension is 2000 over cos 30, which if you track in a calculator, remember to keep your angle in degrees, you should get 2309.4 newtons. Okay, now let's deal with the horizontal direction. And let's use the right-hand side as positive. That's why I've kind of put the right-hand side in a bracket here. Then what can we say? Well, we have a force, but then the force should be balancing on the left-hand side, this T sine 30. Okay, this is great because we know T now, so we can figure out F. F is going to be equal to 2309.4 times sine of 30. You can chuck that in a calculator and you'll get 1154.7 newtons. In other words, roughly 1,200 newtons. All right, smashed it. So now we're kind of ready to talk about the other law, Newton's third law. Once we know about Newton's third law, we're going to be able to combine it with the other two to start solving even more interesting problems. Okay. So Newton's third law. This is kind of a funny one. Newton's third law states that every force comes with an equal and opposite reaction force. Okay, so this seems like kind of a mystical thing. Let's look at some examples. So one example is the kind of feeling I might feel if I were to do something like punch a wall. So we've got this diagram on the left-hand side where I press my fist into a wall. I'm certainly exerting a force on the wall, but that wouldn't explain the fact that I could feel myself pressing my fist into the wall. The reason I can feel my fist pressing into the wall is because the wall is exerting a force back on my fist. It's that equal and opposite reaction force. So someone pushes their fist into a wall, the wall will push back, and that's the actual feeling of pushing it against a wall. Okay, so in contact situations, it tends to be quite simple to identify the reaction force. Here's kind of a more interesting example. Imagine I have some object above the Earth. It has some mass. We all know it will be attracted towards the Earth due to gravity. That's the thing that we called the weight before. What is the reaction force in this situation? The Earth is exerting the force of gravity on this little mass. Where is this equal and opposite force that arises from Newton's second law? Does anyone know? It's kind of a funny one. It's something we can often kind of ignore in our day-to-day lives on Earth, which is why it's slightly less intuitive. Notice this object is not on any kind of a surface, so it's no kind of reaction force in the sense of like a contact force that we were talking about before. What's actually happening here, and you'll see this later if you look at Newton's law of gravitation, is that when one mass exerts a force on another by gravity, it's true the other way around as well. So there is an equal and opposite force where the little mass is exerting the exact same force in the opposite direction on the Earth. So that is the equal opposite, quote, reaction force here. The mass is pulled towards the Earth just as hard as the Earth is actually pulled towards the mass due to gravity. Okay, cool. Now let's go back to these contact forces because they occur a lot in day-to-day life. And so it's really good to essentially get used to reasoning about them. So normal contact force is specifically the kind of reaction force that you get due to a body in contact with a surface. The reaction force from contact with a surface. Okay, so we saw this on the left-hand side here. Pressing your fist against a wall would be one example. Another would be an object which is just sat on the ground. It's being pulled down due to gravity. That's true. It pulls the Earth back up, but also it's being pulled into some surface that it's on. So it's pushing on the surface, and as a result, the surface will push back with some reaction force. And essentially, the surface will push back however hard the block is pushing on the surface. So in this situation here, we got a 6 kilogram mass, so it's got a weight of 6g, pulling it into the surface. And imagine someone else is also just pushing their hand into the block here to push it down even harder. Then since this block is not moving, Newton's second law would say the total force is 0. So in this situation, we'd be able to say that the reaction force, the upwards thing, must balance all the downward stuff, which is the 8 plus the 6g. You could chuck that in a calculator and you could actually figure out what the reaction force is in this case, and it would be 66.86 newtons. Okay, so you can do calculations involving reaction forces. Often they become particularly handy, or they're particularly important to keep note of when you have objects on slopes. Once you're dealing with things that are in various directions, then it's more important to remember a particular feature of reaction forces with surfaces, which is this normal contact force is always directed perpendicular to the surface. Now, in some cases, you might not even think about this. For example, in this diagram here, I drew this reaction force going directly upwards. And you probably didn't even question that, but I was actually secretly using this rule. I drew the reaction force perpendicular to the surface. Now, it's a little less clear when your object is on some kind of a slope. And that's when we need the rule. We need to keep it in our heads. The reaction force is going to be perpendicular to the surface. So that tells me to draw the reaction force like this time. Okay. So once we know this rule, we're in a position to do all sorts of useful calculations. So let's take a look at an example. Let's say we're told this box here is going to remain in contact with a slope. We're asked to find the reaction force. We've drawn it, but we don't know how big it is. We know the direction, but we just don't know the size. We're asked to find the reaction force, and we're also asked to find the acceleration. Now, we're being told here that the box is going to remain in contact with the slope. So I think an important question to ask you all is, what direction is this acceleration going to be? If the ball remains in contact with if the box remains in contact with the slope, what direction is the acceleration going to be? So for those doing physics, what direction? Yeah, so there's a weight going downwards. There's loads of forces in this picture. There's something going up the slope. There's something going horizontal. There's something going down. There's something going perpendicular to the slope. Yeah, loads of things, right? So I'm going to tell you that the sentence is the only thing that will tell us here. Yeah, good. It is up the slope. Now, it may have also been down the slope, but along the slope for sure. And that is just because it says it remains in contact with the slope. So what that tells me is in this direction, the direction of the reaction force, in fact, well, currently it's not moving in that direction. If it stays on the slope, it's always going to be perpendicular to that. It's never, if it stays on the slope, it's never going to go further or less far in that direction perpendicular. So there is no force. The resultant force in that direction must be zero. It's not moving off the slope. So it's essentially staying at rest in that direction. So the only direction there can be any kind of a force is along the slope. Any kind of a resultant force and any kind of an acceleration that can only be along the slope. So this is a very important rule. When you're told something remains in contact with the slope, that means perpendicular to the slope, the resultant force is zero, and the only movement will be along the slope. Okay, so first of all, let's find the reaction force. And remember, one of the things we just said there is that perpendicular to the slope, we know that the total force resultant force is zero. General rule for motion on a slope, resultant force equals zero. What does that tell us here? Well, we have R in that direction. It's totally going away from the slope. But we need to figure out what forces we have in this other direction, which must be balancing the reaction force. So what do we have? Well, there's a couple of forces going on. There's this 5 Newton force. We need to find the component of this 5 Newton force perpendicular to the slope. In other words, we need to find this bit here. Okay. Well, if this angle here is 30 degrees, we have another angle of 30 degrees here. And using the kind of opposite rule for trig, the component of the 5 Newton force perpendicular to the slope must be 5 sine 30 degrees. Okay, so trying to take us off the slope is the R and the 5 sine 30 degrees. Then what is it that's keeping us on the slope, pulling in the other direction? Well, it's some part of the weight. So let's draw the weight here. I drew a slight curve, that's just by accident. We've got the weight, and it's made of 2 parts, the bit that's along the slope and the bit that keeps us stuck to the slope. So we've managed to draw this little triangle here. And a classic rule that you'll want to remember for these kinds of problems is that if this angle here is 30 degrees, then this angle here is 30 degrees. Okay, something we probably won't have time to show now, but if there's a little time at the end, I can come back to it. It's worth drawing this diagram yourself and seeing if you can check that. Okay, so then putting us onto the slope, we've got the weight and we've got cos of this 30. Weight times cos of 30. That's what must be making us have a resultant force of 0. So the weight is mg, so it's mg cos 30. And we know the mass, it's kind of been obscured here, but it was 0.3 kilograms. So let's write that here, m equals 0.3 kilograms. Okay, so we can use this to calculate the resultant force. It's 0.3 times 9.81 times cos of 30 minus 5 sine of 30. Okay, chuck that in a calculator and you get a resultant force of 12.79 newtons. So using Newton's laws, we've already figured out that the reaction force is exactly this many newtons. Now we're being asked to find the acceleration. And again, we're not moving off the slope, so the only acceleration will be along the slope. So now let's use Newton's laws along the slope. And what forces do we have to deal with there? Well, we know we have F equals ma to start with. So ma is going to be the resultant force. But what is the resultant force? Well, we've got 6 newtons pulling us up the slope. And whoever said up the slope, that was actually exactly correct, I think. Yeah, I think the downward force is less. Actually, let's check. Okay, so up the slope, we have 6 newtons. And then we need to take away anything that's pulling us down the slope. Well, there's that 5 Newton force, and it has a down the slope component, which is this bit here, and that's 5 cos 30. So we need to take away 5 cos 30. And then also we need to take away the component of the weight that wants to pull us down the slope, which is this W sine 30 here. So that's 0.3 times 9.81. That's the weight, times sine 30. Okay, so that's one big number now. And that's what ma is. We could find the actual acceleration just by dividing all of this by the mass instead. And the mass was 0.3. So you can chuck that whole thing into a calculator. It's a pretty big looking expression, but that's no worries. And you'll get around 0.66 meters per second squared. Interesting question to ask yourself is, what direction is this acceleration? There was this thing, you said up the slope, and I said, well, maybe it could be down the slope, but it's certainly along the slope. Well, you were absolutely right. I phrased everything that was up the slope as positive. Everything that was down the slope was negative. And the acceleration I got, the answer was positive. So that means it must also be up the slope. Good. Okay. How are we feeling? Has anyone got any questions? Seeing a 1. Awesome. Seeing a 1, a 2. Okay, very nice. As I was saying, ask if there are any questions. Good news is we have some exam questions to look through as well, which very much reviewed this last point in particular. So let's chat through this. We might even have some spare time at the end. Okay. So let's take a look at this question. Figure 2 shows a sledge moving down a slope at a constant velocity. It's going to be a really common theme in exam questions, object on a slope. The angle this time is 22 degrees. There's 3 forces and they've drawn them all in the diagram. That's handy. There's a weight, a friction, and a reaction. And then they say, with reference to an appropriate law of motion, explain why the sledge is moving at a constant velocity. This is kind of a funny question. They're basically asking us to tell them a piece of course knowledge. And the bit of knowledge they want is, what is it about forces in Newton's laws that would make something move at a constant velocity? What does that tell you about these forces? So, what does it tell me? If I tell you this object is moving at a constant velocity, what can you tell me about the forces? One of Newton's laws tells us something about the force when we have constant velocity. Good, nice. The forces are balanced. The resultant of all these forces is equal to 0. Yeah, I really like both of these answers. Yeah, awesome. Really nice. So with a reference to an appropriate law of motion, there's 2 marks here. So I'm going to mention a law of motion. I could choose the first or second law to explain this. In each case, I need to state the law and then explain in terms of it. Okay, so I'm going to use the first law. I'm going to say the resultant force is 0. So by Newton's first law, we know that the velocity will be constant. Now, there's a lot of space there. That's partly because the explanation with Newton's second law, which you could have chosen, might have just taken a little bit longer. But explaining it in terms of Newton's first law is nice and quick. Okay, good. So now we've got a load of technical questions about this situation. So I think it's probably best if I just redraw this diagram. We've got the 22 degrees. Okay, there we go. 22 degrees. We've got an object, doesn't matter what shape it is, and there's a weight. I guess there was a reaction, and there was like a force up the slope, I believe. Let's just check. Yeah, looking good. The mass is 4.5 kilograms. Okay, calculate the component of the weight parallel to the slope. Okay, so I said that if this is 22 degrees, that means that this thing here must also be 22 degrees. So what trig function should I use to find W, but the bit in this direction, parallel to the slope? Got this 22 degrees, and opposite to it is the parallel to the slope direction. So which trig function should I use? Sine or cos? If it's the opposite to the angle. So sine, yeah, nice. Sine is opposite, really good. And then cos is the adjacent. Oh, it looks like I lost my pen. There we go. Okay, so this component here is W sine of 22. That's the bit that's going along the slope. Okay, so we're going to take mg sine 22, which is going to be 4.5 times 9.81 times sine 22. Whereas remember to keep your calculator in degrees, not radians here. And you should get around 16.57 or roughly 17 newtons. Then we're asked to find the component of the weight perpendicular to the slope. Okay, well, that's the other one, this one here. And since we used sine before, this one must be cos. Good. Okay. So this time perpendicular to the slope, we've got the cos part of the weight, which is going to be 4.5 times 9.81. That's the weight. Then taking the component, really key technique to have for these force questions. It's multiplying by cos 22. Chuck that in a calculator and you'll get around 41 newtons. Okay, good. Now, finally, we are asked to state the values of F and R. Okay, so let's start with F. Remember, this object is moving at constant velocity, and that told us something about the forces. So keeping that in mind, what is F? Got a weight pulling down here of 17 newtons. We've got a weight in this direction here, and that weight is going to be 41 newtons. We know we're in equilibrium. So what is F? If the total force along the slope is 0, yeah, good. Total force along the slope is 0, good. So if there's 17 pulling us down the slope, there must be 17 pulling us up the slope. The only thing pulling us up the slope is F. So F is 17 newtons. And what about R then? We're also not moving off of the slope or crashing and making a dent in the slope. So the total force perpendicular to the slope is 0. So what is the reaction force? Good. The reaction force is 41 newtons. Perfect. Good. 41 newtons. Okay, really nice. So you should now be able to state and explain Newton's three laws. You should be able to calculate, yeah, really nice, good. You should be able to calculate resultant forces and determine if a system is in translational equilibrium. And you should be able to solve problems involving weight and reaction forces. All right, so hopefully that is all making sense. Does anyone have any questions? Just while I'm taking a look at the chat to see if there's any questions, I will mention, by the way, that as I said at the start, I've come here from Snap Revise. So on Snap Revise, yeah, absolutely no worries. Thanks very much, everyone, for coming. So on Snap Revise, we've got all sorts going on at the moment. But we do a lot of, oh, that was already clear. Great. Lots of marks for little calculation. Yeah, that's true. So on Snap Revise, we've got a load of different styles of revision course, actually. So we have video courses for all of A-level and GCSE physics. And alongside the video courses, we've also got revision guides that you can use and all sorts of mock exam questions we've come up with, videos of us going through exam questions using our own techniques, explaining how we would actually think about answering exam questions. And we have this kind of thing going on where you can take quizzes, and the quizzes will actually highlight which bits of the course are the bits that are most worth you spending your time on as well. So that's just a little note about Snap Revise. I managed to cover all your school content, which you're finding really difficult to understand. You'll check out the vids. Amazing. That's really nice to hear. Okay, so I'm actually off to go do some stuff in Snap Revise right now. So I've got to shoot off. Thanks very much, everyone, for coming. That was really fun for me. And I'll see you all at the next one. Okay, bye.